Welcome my dear students, new session. In this class we discuss about the general method for finding eigenvalues and eigenvectors. In the last class we use finding the eigenvalues and eigenvectors by the method we just write ax is equal to av is equal to lambda v, or av is equal to lambda v. We finding the vector right in the form of we take any vectors x and y up to xn, and then we take a find the value for lambda corresponding to the eigenvalues of this. So now we have to find, it is very difficult to find a if we have a matrix more than n by n matrix, not a 2 matrix. 2 by 2 matrix is the simplest way we can calculate by the eigenvalues of this by the method previously. Now we find what is the general method for finding the eigenvalues and eigenvector now we discuss general for finding if A is n by n matrix, then we have by the definition AV is equal to some lambda v. For some lambda is equal to 0, if and only if, this means can say that AV minus lambda v is equal to 0. That is, we can say that AV minus lambda v is equal to 0 means we can say that this can be written in the form of a minus lambda I. So this can be written as a v minus lambda iv identity matrix is equal to 0. Then we can say that a minus lambda I into v is equal to 0. Now this system is a non-trivial solution on the case when we have a determinant of a minus lambda is equal to 0. So we know that the equation has a non-trivial, this equation has a non-trivial solution if and only if determinant of a minus lambda is equal to 0. So if the determinant of a minus lambda is equal to 0, then the system has a non-trivial solution. So because for this we have to find a non-trivial solution, because we have to assuming that v should be a non-equal to 0. For v is equal to 0 is we have getting the trivial solution. So we are excluding the case for the trivial solution. We have to try to find the only the what is the general non-trivial solution of any linear this eigenvalues and eigenvector corresponding to the eigenvalues. So that means we can say that general method, we can say that find the determinant of a minus lambda is equal to 0. So general method is say that you have this system has a non-trivial solution if and only if determinant of a minus lambda is equal to 0. So we summarize this in the form of the lambda is an eigenvalues for the matrix A if and only if determinant of A minus lambda is equal to 0. Now the equation a determinant of A minus lambda is equal to 0 is called the characteristic equation of the matrix A, and the expression determinant of a lambda minus A is called the characteristic polynomial. This is denoted as a suppose P of lambda can be written as a determinant of a minus lambda I is called the characteristic polynomial of the matrix A. So this means we can simply say that we have any matrix, for example A is equal to, you have a 1 minus 1 and 2 4, then if you ask you what is the characteristic equation for this, characteristic equation means we can calculate a determinant of a you have a 1 minus lambda minus 1 2, then you have a 4 minus lambda, and then you can say that, or just we can write in there. So we have to write in this form. We can write A is equal to, you have a 1 minus 1 2 and 4 minus lambda times you have a 1 0 0 1, and then we calculate this is the determinant of this should be is equal to 0. So we can say the determinant of you have a 1 minus lambda, and you have a minus 1 2 4 minus lambda, and this should be is equal to 0, and this equation is called, now we have to simplify this. You have a 1 minus lambda and 4 minus lambda and plus 2 is equal to 0. Then this simplify further, we can say that lambda square minus 5 lambda plus 6, we have a, this is equal to 5 plus 6 is equal to 0. This is the equation into the, this is a p lambda, and this is called as the characteristic polynomial of this matrix and corresponding this, and this equation determinant of a minus I is equal to 0. This is called as the characteristic equation of the matrix A, and this is a polynomial. This polynomial is called as the determinant of A minus, this is the polynomial. This polynomial is called as the characteristic polynomial of the any matrix A is given into a this form. So if the this is the characteristic polynomial of this matrix, and then we have to just say that. So if n by n matrix, lambda is an eigenvalue, so we set the v lambda is the form of a is collection of all the a minus lambda is the form, v is the element of a, and this is called as the eigenspace. So this means we have to just say that for each lambda we have a lambda 1 is equal to some v belongs to the Rn, such that av is equal to lambda v, and then we can say that clearly this is non-zero, this term is a v should be not equal to 0, is called the eigenspace of this of a matrix A corresponding to the eigenvalue lambda. So this way we can say that this is a general method. We have any matrices giving, first we calculate the characteristic equation of this. By the solving the characteristic equation we get the characteristic polynomial. Solve this characteristic polynomial, we get the value for a because this is we have to denote as a p lambda, and we have solved the characteristic equation lambda polynomials by the lambdas for the value of a lambda, and then this value of a lambda we can, with the help of this lambda, we can calculate the eigenvector corresponding to the this. Okay, so this means v lambda is a union of the set of all eigenvectors corresponding to lambda and the 0 vector. So this means v lambda is nothing but is equal to union of a, we have a whatever eigenspace you have to calculate, this is nothing but is equal to union of a 0 subspace also, because 0 is also one of the solution but is a trivial solution. When we have said that the v lambda is nothing but is equal to union of a, this means we can say this is nothing but is equal to union of a 0 also. So this means 0 subspace means we can say simply is equal to 0 is the, we can in this case we have a trivial solution of this given equation. So that's the reason we can say that this is the case we have to say this is the for finding all this things that is possible. Okay, so now for any scalar lambda is equal to v, this can be written in the form of a av minus lambda v is equal to 0, then this can be written as av minus lambda v is equal to 0, then a minus lambda v is equal to 0, then v is nothing but is equal to, you know that if we have a this A is a matrix, then it is also form a transform. If it is to form a transform, then this means we can kernel of this, and now we have to, this is some transformation into v is equal to 0. That means if transformation is v is equal to 0, that means this v is the belongs to the kernel of that person, that's t, and this is t is in place of a, we have a v is the element of a kernel or kernel of an a minus lambda I. So kernel is also denoted as a either kernel of a this, or we can say that n of a this. This is in place of n, you can use a kernel also. So this means v is the element of a that is kernel of a minus lambda I. So if we can say that into this form, this means clearly by this v is the element of a, whatever this is eigen vector we have to calculating this eigen vector is calculated. This is also belongs to the, means we have a null kernel of a minus lambda I should be is equal to, because the system of equation. Therefore the eigenvectors of a with the eigenvalues lambda, if any are the non-trivial solution of the matrix a minus lambda I is equal to 0. So non-zero vector in a minus lambda I, a kernel of a minus lambda I, and if this equation has a non-trivial solution, then lambda is not a, if it has a no, this is very important, if it has a no non-trivial solution, then lambda is not an eigenvalue of a. So we clearly say that this is a non-zero vector of a kernel of a minus lambda I, and if the equation, if I simplify this equation, if this equation has a no non-trivial solution, if this equation has a no non-trivial solution, then lambda is not an eigenvalue for this matrix A. So this is clearly, we can say that if we have a given vectors and that vectors has then a no non-trivial solution, then we can say that this lambda is not an eigenvalues of a this corresponding this. Now the above observation is important. Why? Because it's saying that finding the eigenvectors for a given eigenvalue means solving the homogeneous system of equation. That means we have to giving the some such a homogeneous system of equation. And now we show that that means we have to just show that this v lambda we have to define as the form v lambda is in the form of this. So v lambda is equal to, we have to just say that I writing here. So v lambda we have is the form of a v in the form of a Rn, and then such that a of v is equal to lambda of a v. Now we have to show that this V lambda is a subspace of a Rn, because you know that this V eigenvector is the element of a kernel of a minus lambda I, and kernel is a subspace. So this means clearly V is also is a subspace. So this means V is the element of this set V lambda, and V is the element of a V lambda, and that means V lambda is also a subspace. Now we have to try to show that this V lambda, we have to the eigenvector eigenspace is also a subspace of a Rn. So now we have this is clearly is a non-empty, because we have at least one trivial solution is already exists. So this means this is a clearly we have to just say that, because V lambda can be written as a this is the this set and the union of a 0. So this means this clearly is a non-empty set. Now we just show that it is a closed under vector addition and a vector scalar under the scalar multiplication, and also the under closed under addition. For scalar multiplications is already we have to show that, if you remember, we can just say that A times of a C of V. This can be written as a, you have to just say that A C times of A of V, and then we can say that we can write in the form of a, this is a AV is equal to lambda V. So C times of a lambda V, and this can be written as a lambda times of a CV, and this we can say that CV is also the element of a V lambda, because we have to show that A of CV is equal to lambda times of a CV, then CV is the lambda of a, this means this is closed under the scalar multiplication is closed. So now we try to find the show that the we take two vectors and v1 and u or v, whatever this you just check. For example, u and v are the element of a V lambda, then you can say that a u is the same as a lambda u, and a v is the same as a lambda v. Now we show that u plus v is also the lambda of this term. We can show that a times of a u plus v, a plus u plus v means we can say that by the matrix addition, a times of a u plus a times of a v property of a matrix, we can say that this is sorry, a times of a v, and now a of u is equal to, you have a lambda u, and a of v is equal to, you have a lambda v, and then this can be written lambda times of a u plus v. So a of u plus v is equal to lambda times of a u plus v, then we can say that u plus v is the member of v lambda. So that means we can say that we already show that C of v is the lambda of lambda v, and u plus v is also the member of lambda v. So this means we can say that this is clearly, we can say that this is a satisfy both the condition. So this means this is a clearly this is a satisfy under addition and scalar multiplication is a closed. So this means V lambda is clearly is a subspace, and this is a subspace of a Rn. So this means we have to prove that this successfully, that this is a subspace of a this thing we just said that. Okay, this is a complete the solution. That means we can say that this whatever V lambda we have to choosing, this V lambda is nothing but is equal to is a subspace of Rn. So this V lambda is a subspace of a Rn. This eigenspace is a subspace of a Rn. Now this V lambda is nothing but is equal to, we can say that a minus v, then this is equal to 0. This means this is nothing but is equal to kernel of a, we can just kernel, I denoted a kernel as n. So a minus lambda I. So V lambda is a null space of a matrix A minus lambda I is a subspace of a Rn. So V lambda, again we can V lambda written in this form, and then you can know that this is the clearly is a subspace. So this means this way we can also say that this is a V lambda is a null space of the matrix A minus lambda I and is a subspace of a Rn. We have to just prove that. Okay, so now we have if lambda is equal to MB matrix and lambda is the eigenvalue of A, then lambda eigenspace of A is the solution of A minus lambda I into V is equal to 0. So this is a subspace of this. This means for finding the value for this eigenvector, we have a corresponding to the lambda is equal to some lambda. We have to solve this this homogeneous system of equation. Then if this homogeneous equation is a non-trivial solution of this homogeneous equation, by this find the value for this V, and that V is called as the eigen space of this means we can V lambda is solving this. So this means, and by n matrix lambda is the eigenvalue of A, lambda eigenspace of A is the solution of the this set, we can say that. So this means this way we can complete this way. So now just and now we established by this all this combining all this thing we have discussion in the form of a theorem. That means we can say that if A is an n by n matrix, lambda is a scalar, then the Fowler statement are equivalent. Lambda is the eigenvalue for A. If lambda is the eigenvalue of A, that means this system has a non-trivial solution. And if this system is a non-trivial solution, previously we showed that the null space is clearly is not equal to 0 space. And if A lambda is a singular, and then we can say that also the determinant of A is equal to 0. So if we have just as A minus lambda is equal to singular, then determinant of A minus lambda is equal to 0, and A determinant of A minus lambda is equal to 0, then lambda is an eigenvalue of A. So this means this is all are the connected itself. This is proof is very trivial. I am not interested to prove this. This is very trivial. If lambda is an eigenvalue of A, then clearly A minus lambda x has a non-trivial solution by the definition. And if A minus xi is a non-trivial solution, by the previous discussion we can say that null kernel of A minus lambda is clearly not equal to 0 subspace. And also if A minus is not a 0 subspace, means it is not a 1 1, and then clearly if it is not 1 1, this means not a non-singular. So what is non-singular means is a singular. So this means clearly by this we can say that this is a singular, and if this is a singular, then determinant should be is equal to 0. So this is clearly by the all the statements are equivalent. So this means we can find a lambda is eigenvalue, means if this any one of them we can find the null space of A minus lambda I and show that if it is not a 0 subspace, then we can say that that is this lambda is an eigenvalue of a corresponding value for eigenspace, and then we have to calculate this. Okay, now we just try to start with one example and discuss this example. So in very detail, we have to just say that find the eigenvalues and corresponding eigenvectors of this give the description of the eigenspace corresponding to each of the eigenvalues. So I just say that we can write in the form of a determinant of A minus lambda I should be is equal to 0. We write a characteristic equation of this. So determinant of A minus lambda is equal to 0. So now we have to just take solve this is should be is equal to 0. The characteristic equation of this we have to solve this. So we can say that 2 minus lambda and minus 5 minus lambda, and then you have a minus plus 12 is equal to 0. Then you can say that you have a multiplied by you can multiply by 2, so you have a minus 10 minus 2 lambda plus 5 lambda plus lambda square plus 12 is equal to 0. Then you can say that lambda square plus 3 lambda, and then you have a plus 2 is equal to 0. Then you have to we have a lambda square, we have to take a 2 plus 1, then we can say that we have a 2 lambda plus we have a lambda plus 2 is equal to 0. Then we have a lambda times lambda plus 2 and 1 times lambda plus 2. So this means we can simplify this. We can say that lambda is equal to minus 1 and lambda is equal to you have a minus 2 are the two roots of this. So this we can say that. This means we can say that, so lambda is equal to minus 1 and lambda is equal to minus 2 are the two roots of this given system of characteristic equation. And now we can find the eigenvectors corresponding to lambda 1. So lambda 1 is equal to minus 1. So you have a minus this is equal to you have a minus lambda 1 is equal to you have a this thing. So we have to solve the system equation. We have a 3 minus 12 1 and minus 4, and then we have a x and y is equal to you have a system equation 0 0. So we can say that 3x minus 12y is equal to 0. Then you have a x minus 4y is equal to 0. Then clearly we can say that from the second one we can say that x is equal to you have a 4y, and then simply x is equal to 4y is here. So you can say that v of lambda 1 is nothing but is equal to in the form of a we can say that in the written as the form of a we write in the form of a y is equal to t. So this x is equal to 4t. Now 4t comma t transpose some that t is the element of a some real And then similarly in the fashion we can try to find so this is equal to, you have a span of a kernel of a plus I is equal to span of a 4 and I. Why I just I explain to you. So the eigenvectors for v1 is equal to 4 comma 1, because we can write kernel of a plus I can be written in the form of a, this is the v lambda 1, this is nothing but is equal to, we can write in the form of a, I just said that in the form of a, you have a 40 and t such that t is non-zero, t is the element of a R. And now this is the spin of a this thing. Okay, now we try to for lambda is equal to 1, then lambda is equal to 1, you can say that we have a lambda is equal to 1 means a minus lambda 2I is equal to, you can say that a minus I. So a minus I is equal to, you can just say that you have a matrix is, you have a like this, you have a this matrix, we have a 2 and 2 minus 12, 1 minus 5, so 2 minus 12, we have a matrix like A is equal to 2 minus 12 and 1 minus ka 5, and then you have a minus ka I, and this is nothing but is equal to, you have a 2 minus I means you can just write a matrix 1 0 0 1, and this means we can say that 1 minus 12, then you have a 1 and then you have a minus ka 6. So we can say that x minus 12y is equal to, if we write a xy, calculate is equal to, you have a 0 0, and then this is equal to 0, then you have a x minus ka 6y is equal to 0. So this means you can say that I'm sorry, this is somewhere mistake, maybe okay, this is equal to 4t1, and then this can be written as the v1 and s plus 4. Okay, this is plus 2, oh sorry, I am calculating minus 2. So lambda is equal to, we have a lambda 2 is equal to minus 2. Sorry, I'm sorry, I've just calculated minus 1. So actually lambda is equal to minus 2. So this is equal to this, so we can write 4 and minus 12 and 1 and minus 3, and this is the, we can write x and y is equal to, you have a homogeneous system of equations. We can say that 4x minus ka 12y is equal to 0, then you have a x minus 3y is equal to 0. So this implies that you can say that x is equal to, you have a 3y. So this means we can say that v lambda 2 is equal to, if we take a lambda is equal, this is nothing but is equal to in the form of a set, you can just say that in the form of a t times of y is equal to t, then x is equal to 3t, so 3t and t, and such that you have a t is the element of a R, and this can be written as a we can write in the form t times of a, you can 3 and 1, then you can say that such that t is the element of a R, and then we just say that this is v of lambda 2 is equal to span of we can say that span of, you have a 3 and 1, and then we can say that this is clearly, so this is the eigenvector of this corresponding to this is equal to, we can say that 3 and 1 is one of the eigenvector of this v2, and then we can say clearly v2 is nothing but is equal to t times of a lambda 2. Eigenspace can be written in the form of this is eigenvector, so eigenspace in the written in this form, this is the eigenspace of a this solution. Okay, so now we just try to one more example for this. We try to find the eigenvalues and corresponding eigenvectors of a is equal to this 2 minus 12, 1 and minus 5. Give the description of each eigenvalues and eigenvector. So we try again, we with the help of a, we can first start with the determinant of a eigencharacteristic equation of a determinant of a minus lambda I. Now we calculate a minus lambda I. So a minus lambda I is equal to, you have a 2 minus lambda minus 12, 1 minus 5 minus lambda. Okay, this is the this way we can just take into this form. Okay, this is the same solution I just solved right now. Sorry, this is the repeat. I will skip here. Okay, now just come to this problem. Okay, so we just that this is the another problem. We just take in the form of a calculate the determinant of a minus lambda I eigen characteristic equation of this, and this way we can just, this is written in the form of a, we have a, this is minus lambda 1 0, then you have a 0 minus lambda 1, then you have a 4 minus 17 and 8 minus lambda, and then we can calculate and show that this determinant now determinant of a minus lambda I is equal to 0. So this means this is equal to 0. Now we have to simplify this. We just take into this forms. We have a minus lambda, then you have a minus lambda 1 minus 17 8 minus lambda, and then we have to go to the plus 4 times, or just we go to the plus minus 1 times minus 1, this is gone and this is gone. So you have a 0 1 4, and then you have a 8 minus lambda is equal to 0. So this is minus lambda times you have a minus lambda 8 minus lambda, and you have a minus minus plus 17, and then you have a, this is 0, so you minus 4, and then minus minus plus 4 is equal to 0. So this means this way we can write into this form. So this is simplify this, we can calculate here. Just you have to lambda minus plus, so lambda square, so you have a lambda square, then you have a clearly you have a lambda square 8 minus lambda, and you have a clearly you have a minus 17 lambda, and then you just this is plus 17 lambda. Okay, so this means this way can just this is minus minus plus. Okay, so we simplify this, you getting this way clearly this is lambda cube 8 lambda square plus 17 lambda and minus 4. So eigen values must be there for the this cubic equation. For this I denoted as equation number 1. This is the x lambda cube minus 8 lambda square plus 17 lambda minus 4 is equal to 0. This is the, now we have to find the, how to find the solution of this lambda. Then to solve this equation we will begin searching the integer solution. This take the simply the exploiting the fact that all integer solution, if are any of the polynomial equation integer coefficient, if this coefficient, then x to this is the must be divisor of the constant term. Then we know that we can find any solution of this. That means one of the solution can be find this, the constant term must be divisor of the constant term. So if there is any integer solution exists for such any polynomial equation with the integer coefficient, must be divisor of the constant term. So now in this case we have a constant term is equal to 4. So the divisor of the 4 you have a plus minus 1 plus minus 2 plus minus 4. So we can just find the divisor of this is, you have now the divisor of this is equal to plus minus 1 plus minus 2 plus minus 4. These are the 6 possible divisor of this. So we just say that we have equation is this. So the possible divisor of this is equal to, you have a lambda is equal to plus minus 1, lambda is equal to plus minus 2, lambda is equal to plus minus 4. If we substitute lambda is equal to 1 here, then clearly this is not the solution of this, because lambda is equal to 1 is not. So 1 cube minus 8 1 square plus 17 into 1 minus 4 is not equal to 0. So lambda is 1 is not possible. Similarly lambda is equal to this is lambda is equal to 1 is also not possible, minus 1 is also not possible. Now we try to lambda is equal to 2. Now take for lambda is equal to 2, you have a 2 cube is equal to 8 minus 8 into 4 and plus 17 into 2 and minus 4 is again not equal to 0. So lambda is equal to 2 is also not possible. Similarly lambda is equal to minus 2 is also not possible. Now we try to lambda is equal to 4. Then lambda is equal to 4, this is possible, but lambda is equal to minus 4 is not possible. So this means we can say that this is this value. So the lambda is equal to 4 is an integer equation, and hence if lambda is equal to equation integer equation, then we can say that lambda minus 4 is one of the root of this. So lambda minus 4, and we can say that lambda minus 4, and then can be written in the form of a we just write a lambda square. So this is a lambda cube minus ka 4 lambda square, and now you have a plus ka minus ka 4 lambda. So you have a minus ka 4 lambda square minus plus ka 4 to the 16. You have a lambda and you have a plus 1. So you have a plus ka lambda minus 4. You have to simplify this, you getting this equation. So this means we have a solution is lambda square. One of the solution is a lambda minus 4 and another is a lambda square and minus ka 4 lambda and plus 1. So this means we can say that into this form. So lambda square minus 4 lambda plus 1. This is the another solution. Now we have to try to factor this. We have to following this lambda square minus 4 lambda plus 1. So we try to find this solution, and then you know that this is equal to, we can say that the solution of a lambda is equal to b square minus so lambda is equal to b square minus b plus minus b square upon a by the quadratic formula, quadratic equation. Then you can just say that you can write in the form of a is equal to minus b plus minus root b square minus 4ac upon twice a. So b is equal to 4. So you have a b is equal to you have a minus 4 plus minus root square 16 minus 4 a into c. 4 into a is equal to 1, c is equal to 1. So you have a 4 upon 2a is equal to, you have a 2. So this can be written as a 4 plus minus root of this is 12 upon 2. So this can be written in the form of you can just say that 4 plus minus root 12 is equal to 4 into 3 upon 2. So we can write in the form of a 4 plus minus 2 root 3 upon 2. So this can means we can say that the root is equal to lambda is equal to, you have one of the lambda is equal to 4, another lambda is equal to, you have a 2 plus 2 root 3, and lambda 1, lambda 2, lambda 3 is equal to, you have a 2 minus 2 root 3. So this is a possible 3 roots are here. So this means we can say that so this we can corresponding lambda is equal to all these roots are there. Now if we want to find the solution of this equation, we can say that we can simplify this equation. We take in this equation we just take lambda is equal to 4. So this means we can say that the matrix is equal to 4 1 0. So we have to, here we can write 4 1 0, and another vector is equal to 0 4 1. So you have a 0 4 1, and another vector we have a 4 minus 17, 4 minus 17, 8 minus 4 is equal to, you have a 4, and this is the matrix, and then we have to write is equal to x, y and z, and this is equal to, we have a 0 0 0, and then we can say that you have a 4x plus y is equal to 0, then you have a 4y plus z is equal to 0, then you have a 4x minus 17y plus 4z is equal to 0. We have to simplify these equations with the help of or we just try to matrix this eliminate for this matrix in the form of a elementary row operation. So this can be written in the form of a divide whole equation. So 1 by 4 0, then you have a 0 4, and then you have a 4 1, you have a minus 17, and you have a 4, and then you can just write in the form of this 1 by 4 0, and then you can just say that this is equal to 0 is 4 1. Now we have a multiply 4 and adding this is equal to 0. So you have a minus 17 plus 1 is equal to minus 16, and then you have a 4, and then again you just write in the form of 1 by 4 0 0 1 1 by 4, and then you have a 0. We have to again divide by 16 is more 4, so we have a more simpler. So this is minus 4, and then you have a 1, and then this is a matrix, and now this can be written in the form of a, again with the help of a, this is equal to make a 0 here. So just take a, or we have to make here 0, whatever this you have to just take, and then we have to try to here 0. So we have to just adding 4 times of this. So 1 by 4 0, then you have a 0 1 1 by 4. Now sorry, this is not true, this is 0 sorry, so okay, correct, is a 0 1 1 by 4. Now adding this with the 4, multiply by 4 and add, this is 0, this is 0, then you have a 1 by 4 1 plus 1 is equal to 2. So this means we can calculate in the form of a 2z is equal to 0. So z is equal to 0, z is equal to 0 means you have a 1 x plus 1 by 4, y is equal to 0, and then so on, simplify, this is equal to this way. Okay, so this is the clearly this we can get as a eigenvalues of a, this is clearly, these are the 4 eigenvalues of a in this case. So now I have to stop this today's class at this point. In the next class we continue the some different types of examples of a finding the eigenvalues, and then we have to find the eigenvectors also, and also discuss some important properties of the eigenvalues and eigenvectors in the next class. Okay, thank you very much for this.